with FPs all over the place. Signatures, the broader they are, the worse they are at FPs. They get too narrow and they start missing everything. So it is a balancing act, but in general, this method produces a lot more false positives than a purely behavioral approach. It's easily defeated by obfuscation. Let's take, for example, MDAC. If you are loading the MDAC control, you're going to either call it by prog ID, or more likely you're going to look for the class ID of that control and load it in your script. So if I'm looking for that particular class ID, and you, instead of doing it once, you concatenate two strings, the first string has the first half, the second string has the second half, my signature is going to completely miss. And there's absolutely no way a signature-based approach can account for all the different permutations for how you can get a particular value inside of a string. So easily defeated by obfuscation, only works on threats that I know about. So those are two pretty big cons. The third method is a purely heuristic approach. And by purely, I mean it's actually a combination of behavioral and static. This one's a little hard to describe, so I'm just going to use examples, and it'll make more sense. If I see a long script of encoded data, or a long string of encoded data, that looks kind of like shell script on your page, I could use that to say, there's shell script on it, shell code on it, therefore it's bad. But that's not really quite enough. I need a little bit more. So if I see shell code, and I see that shell code allocated repetitively in the browser, then I can say almost definitively, you're attempting a heap spray, or you're a terrible JavaScript coder. Mostly, it's a heap spray, right? So that's a heuristic. The next one is the MDAC control. I can't think off the top of my head why you'd ever want to load MDAC, but that in itself is not enough to say, hey, this is evil. But if I see MDAC, and then I see you loading shell objects that should never be loaded inside the browser, then you're a script kiddie using a 4-year-old exploit, and you should really move on. So that one's really easy. This one also has some pros. Success is not required. It will pick up new threats. Now there's a caveat there. It will pick up new threats under categories I already thought about. So I may not know the exploit you're using, but I know I can categorize this as a heap spray. So that's a big plus, because you, instead of building signatures per attack, you build heuristics per attack category. So that's pretty powerful as well. And again, success not required, and that's a big one. Cons. You really need to tear apart IE, in our case, in order to get the data that you need. There's deep hooks in Trident, the render engine, and deep hooks in JScript.dll, the script interpreter. Because I have to be able to log whenever an allocation occurs. I have to be able to log whenever a string gets concatenated. I have to be able to log whenever you do a string.replace. The heuristics that we're looking for in order to make these categorizations are deep within undocumented APIs that require a lot of reverse engineering and days upon days spent looking at IDA. If any of you guys are from MSec, just give me like 20 minutes alone with the source code or even a header file, and I would love you forever. But that's a big con, and it's also prone to false positives. The example that I gave of poor JavaScript code is actually pretty valid. You'll see a lot of cases where someone accidentally sits in a loop and allocates things. Happens, and what usually end up is a crashed browser. So we use probably like a melange of all three to make a determination, because as you can see, every detection approach has its cons. Everyone has its pros, and they dovetail nicely together. If you leverage the pros of one against the cons of another, you can kind of offset and get a good big picture of what's happening. So we can make a pretty reasonable determination of malicious intent by combining all three methods. So API hooking. In order to do any of this, you need to be able to extract a lot of data from the browser while it's running. And I spent a lot of time on this slide. This slide used to be 6 slides. I was going to talk about, okay, kernel mode versus user mode, on disk or in memory, this method versus that method. And I quickly came to the conclusion that would monopolize the majority of my talk, and this isn't really something you're going to be able to learn at a talk. If you want to learn how to hook APIs and write assembly code, there's a lot of resources out there. The white paper has some interesting links, and if you want to come back and talk to me after the talk. We'll definitely get into that. But I don't want to get too wrapped up in this because it's a little bit orthogonal. But I will say we use two technologies, or one technology and one technique. Primarily, we use Microsoft's DETOURS library, Microsoft Research. Basically does in-memory detouring of any API where you know the function signature and the function address. So very easy, programmatically simple, lets me detour whatever I like pretty much on the fly. There's one caveat with that. You can only intercept code execution at the beginning of the API when it enters a function, and that's about it. So if you need data that's only exists halfway through a function invocation, this method will not work. So for that, what we do is we write our own custom hooks and write custom assembly. The basic premise is simple. You go in, you disassemble the library, you find 5 bytes anywhere around the area where you want to analyze data. You punch through, you change those 5 bytes to a long jump off to your own little bit of code, execute whatever you want, replace all the stack, the registers, return everything exactly the way you had it when you intercepted execution, execute those 5 bytes of instruction, and then jump back to where you were. So we only need to do that. It's a lot more work to do it that way, but we only need to do it. We need to do it because of some of the ways the script interpreter in IE was written. There are certain data structures that are only available mid-function call because of poor coding practices, to be honest with you. There's no reason that should ever really happen. That should be in its own function somewhere else. So that's all I'm going to say about API hooking. All right, so we got API hooking. What are we going to hook? Well, the first and most obvious thing to hook is the file system. We need to know what's getting written to disk. We need to know what you're deleting. We need to know what you're writing. And primarily, when we're hooking the file system, what we're looking for is any file write outside of the internet temporary cache folder, speaking in generalities, and looking for anything that looks like an executable. If you've got a PE header in whatever you're writing, I'm probably suspicious about what you're doing. Some of the APIs we hook, now I'm excluding Unicode versus wide, EX, different versions of the same APIs. There's a million ways to do everything in the Windows API, and we'll just talk about the high-level ones. So the first 4 are pretty self-evident. Create a file, read a file, delete a file, read a file. The last one's kind of cute. Some people think they're really clever and say, I'm going to bypass the file system so you can't detect me. I'm going to write direct ioctls to the drive, to any device anywhere I want. Except IE doesn't do that. And if you're trying to obfuscate what you're doing by going directly past the file system, writing ioctls, well, it's really easy for me to say, hey, no, IE doesn't do that. That's bad. So the attempted obfuscation there actually makes it really easy to spot. The next one, it's fuzzy because that's blown up from a 32 by 32 JPEG, the icon, sorry. So we're primarily looking for ASEP key writes here. An ASEP is an automatic system entry point. Basically, if you ever want Windows to launch your code, given a certain event, you find the appropriate ASEP and write yourself in there. That's how, to continue installation, please reboot. What it's doing is it's writing a temporary ASEP key called run once in Windows, and it will run that at the next boot. So this is how malware gains reboot persistence. If I've got a running executable that's malicious, the only way it's going to stick around is if it writes an ASEP key. So when I reboot my machine, it gets to start up again. And we hook all the registry calls for that. So the next obvious one is process creation. There's absolutely no reason that IE should be launching other processes. There's absolutely no reason for IE to do thread injects into existing processes that are running. The one caveat there is IE does a remote thread execution on itself in certain cases. It's really quite bizarre. I'm not sure who wrote that, and I'm not sure what the justification is. Actually, no, I'll take that back. There is no justification for that. It's quite bizarre. And what we hook there is the create process call, which is a generic way from the Windows 32 API of launching new processes. Shell execute, which is the shell equivalent. You'll see a lot of scripts that use this. When exec is a deprecated version of create process, and this one's actually still popular because it has very few input arguments and it's much easier to execute from shell code. There's less prep work you have to do, which makes your shell code smaller. Create remote thread, we already talked about, injecting a thread into another running process. And the last one is ZW-create process, which I just put in there because it's kernel mode. All of these will eventually lead to a ZW-create process. This one's really hard to avoid. You can get really, really tricky and launch a process by linking directly into the process chain, but it's tough and almost impossible from shellcode. Well, I'm not even sure I'm going to say that, but really difficult from shellcode. That would be a tough thing to do. And by shellcode, I mean the actual exploit itself, not the malicious payload that gets run afterwards. Moving on, we also instrument the rendering engine within IE. That's to give us insight into what's happening in the domain object model. If we've got dynamic content being inserted, objects being created and added to the DOM model, we want to pick that up because it helps us de-obfuscate what's going on the page, and it helps us figure out what the script is doing, how it's manipulating the browser. And we hook, none of these will really jump out. These are all internal methods that we reverse engineered, and I think we pulled these names out of the PDBs that Microsoft provides. So these are all just injected, and we try to figure out if any elements are being created, any attributes being set, and so forth. And second last, but definitely not least, we hook the script interpreter. This is how we do all our eval-based de-obfuscation. So there's two eval methods. IE supports JavaScript and Visual Basic as well. And we also pull out common functions that are invoked for obfuscation purposes. Plugins. These are fun. Plugins are responsible for most of our headaches. ActiveX is pure evil. But COM is not. COM is actually quite useful. The fact that it hasn't been sandboxed properly has given ActiveX a really bad name, and that's unfortunate. But on the plus side, it makes it really easy for me to control or instrument every single plugin in the browser. All I have to do is hook the COM libraries. And in order to create a COM object, you got to either go through co-create, get class object, create instance. The last one in there is the IUnknown interface. I don't know how much you know about COM, but in order for any scriptable object to be accessed, you have to query its interface to figure out what method it exposes. And we hook that in order to figure out, okay, what do I need? I'm about to load a binary I've never seen, a plugin I've never seen. I got to figure out how I instrument this binary. And we just basically watch the IUnknown traffic and dynamically instrument. Fun stuff. Okay, so an attack dissection. So we've gathered all of this data. We've got this virtual machine. We're visiting websites. We're doing all kinds of crazy stuff. How does it actually look to dissect one of these attacks? So the first one we're going to go through is the MSO614, the MDAC vuln. And I think this is a single exploit script, not a kit. Oh, wow. Looks like my desktop is an untrusted location. Oh, okay, I'll buy that. There's been a lot of exploits that deal with that, but that's new. So what you have is a big, is that legible out there? All right. So what you have is a big block of text, which may or may not be malicious. This actually, a lot of JavaScript compactors and packers will do things like this, and there's really no way to say this is malicious based on the fact that there's a big block of escaped characters. The variable name sploitia, kind of an indicator, but there's really no way to write heuristics based off of that. Well, maybe not. So what we have is a big block of escaped characters. And as you can see, there's a simple double while loop going through and doing a from char code for each one of those characters. I don't think this does anything. This date.search and date.parse, I think they're all going to return true. And it's basically making sure that it's not pulling, it's basically extracting all the percentage signs out, getting those numbers, extracting a char code from one of those numbers, and pulling it in, and then doing a document.write, one letter at a time, to the domain object model to basically get the script to execute. So if you were trying to figure out if this is malicious, it would be kind of annoying, right? I mean, this is a big block of something. I have no idea what it's doing. If he hadn't named the variable sploita, then I wouldn't know if that was malicious or not. So the first pass at de-obfuscation. All right, so I hooked document.write. And now that I can see, okay, that big block of something is actually a script block because it's writing script, language, equals JavaScript.